This is just going to be a very general introduction to entropy, giving you a bit of background on why it's important. You don't necessarily need to know all of this. We'll emphasise what you do need to know, and it's there in the notes, but it's just to give you a bit more background about why it matters, and therefore hopefully make you a bit more confident with this topic. If you already feel you understand what you need to understand, then you can go straight into the questions. So, the key idea of entropy lies in this definition, which you do need to know, which that it's a measure of the dispersal of energy in a system. So we need to think about a little bit about what that means. So if you think about a system made up of molecules, each molecule has its own energy, and so the first way in which energy can be dispersed is that it can be shared out amongst the different molecules, rather than, you could imagine it all being focused in a few, which might be whizzing around wildly while the others are sitting still. A more dispersed state would be where it was shared out amongst all of them. But also, molecules have different types of energy. So you can imagine if you have a simple molecule like an H2 molecule, it can have translational energy, which means it can whiz around the room in different directions, but it can also have rotational energy, so it can spin around like that, and it can also vibrate like this. And all these different forms of energy, dispersal means that it's spread out amongst all of these different forms, not localized in one. And the reason we care about that is that if you look at the universe as a whole, not just focus on a local part of it, but if you look at the universe as a whole, the second law of thermodynamics, which is one of the most important principles in the whole of physical science, is that says that the entropy of the universe always increases in anything that happens. So every single process that happens in the universe increases the dispersal of energy. And therefore we can use that idea ultimately to answer one of the big questions of chemistry, which is why do some reactions happen and some reactions not happen? Why are some things feasible and other things are not? And at its deepest level, the answer to that lies in, does it cause the entropy of the universe to increase? If it does, then it can happen. If it doesn't, then it can't. Now there are two problems with that from the sort of chemistry point of view. The first is that it's very difficult to think about the universe as a whole. So what we really want to be able to do is to focus on the local system, like what's in our test tube or whatever it might be. So we want to focus on the system, not on the whole universe. And the second is that we don't really want to have to think about energy and energy levels. That's too complicated. We want to think about particles, because that's really what chemistry is mainly concerned with. So we can deal with both of those by sort of using an approximate version of understanding what entropy is, which says this, that if the particles in a system become more disordered, the energy becomes more dispersed. So delta S is positive. So we can sort of illustrate that with a very simple example. So suppose I have a bottle containing a gas, and I tell you that I'm going to take the top off the bottle. Then common sense and experience tells you that the gas is going to escape from the bottle and it's going to spread out around the room. And you also know that no matter how long you wait, once the gas is spread out around the room, it'll stay spread out. It won't reconverge and make its way back into the bottle. Now, if you think about why that happens, it's not to do with an energy change, because the energy of the individual molecules is the same when they're buzzing around within the bottle as it is when they're moving around in the room. Their energy levels haven't changed. But what's changed is that because they've become more spread out and more disordered, then the energy they carry with them has also become more dispersed. And that's a simple example of where we're going with this. So this may not be completely always true, but it's a good enough generalization that we can use it in chemistry. So you need to know both of these things. If you're asked what is entropy measuring, the answer is that, but all of the actual interpretations of entropy that we'll do are based on that. So one of the things that you have to be confident about doing is predicting the sign of delta S in a given process, which might be a chemical reaction or anything else. And the key to that is to sort of have this picture of how disordered the particles are. So if you imagine a sort of entropy graph like that, the most ordered or least disordered state that particles can have is a solid. So down here at the bottom we've got the solid. And the idea there is that the particles have fixed positions. So there's very little disorder because their mean positions don't change. They may vibrate, but their mean positions don't change. They can't have different possibilities of where they are. So that's a highly ordered state. So solid is the least disordered state and therefore the lowest in entropy. Now, liquid will be a little bit higher, but only a little bit. Because although the particles have more freedom of movement in a liquid, they're still confined to a local region of space. And that is a big limitation on the dispersal of energy. So a liquid is slightly higher in entropy generally than a solid, but it's when you form a gas that you see the big difference. Okay, so the gas is the most disordered state and therefore the highest entropy. But the important thing is that it's not just a bit higher, it's much higher. And that has one very important effect, which is that if a process happens which increases the number of molecules of gas, that's going to dominate everything else. So there may be more subtle changes involving, solids changing into liquids or whatever, but that's going to be dwarfed by the change in the moles of gas. So most examples they ask you about, all you have to do is ask the question, do the moles of gas increase or decrease? And if they do, then you can straight away say increased moles of gas, that's more separate particles wandering around, so the energy is becoming more dispersed, delta S will be positive. If there's a decrease in the moles of gas, that's less disorder and delta S will be negative. It's only in cases where the moles of gas don't change that you have to think about more subtle things involving solids and liquids. So we can just make that sort of generalization that if moles of gas increase, disorder increases. And that in turn means that delta S is positive. Okay, so that's enough by way of a general introduction. So you should now be able to do the first two questions on the entry and free energy question pack. Once you've done those, we can then look at putting some numbers onto that, and you can do the next few questions.